In this video, we'll talk about one-sided derivatives, which are a way we can analyze this limit that defines a derivative in a different way, and allow us to be more specific about why certain derivatives do not exist. So we have a limit that defines the derivative normally, and this limit may or may not exist. We can also think about it as one-sided limits, where I only let h be positive and go to 0, or negative and go to 0. This lets us think about what are called one-sided derivatives, and then we can talk about functions being differentiable on closed intervals, as well as why certain derivatives don't exist at point. So for definitions, we say that a function f is right differentiable at x if the limit here where I take it from the right exists. Similarly, we say the function is left differentiable if the limit from the left exists. And relating to work on limits before, a function is differentiable if and only if it is both left and right differentiable and the limits are equal. Let's now look at some examples of where this comes into play. Consider the function f(x) is the absolute value of x. I want to find its derivative at 0. So for this, I need to work on computing the limit as h goes to 0 of f of 0 plus h minus f of 0 over h. If my function being the absolute value function, this is the same thing as the limit as h goes to 0, absolute value of h over h, because the f of 0 is just 0. And I want to find this limit. Now there's no way to directly do this because of the fact the absolute value function is piecewise defined, but I can look at left and right hand limits here, looking at if the function is left differentiable and right differentiable. So from the right, we have the limit as h goes to 0 plus absolute value of h over h. But since h is coming to 0 from the right, h is positive, which means the absolute value of h is just h. Limit h goes to 0 plus of h over h, which is 1. And from the left, we get the same idea. But since I'm coming in from the left, h is less than 0, so h is negative, meaning that the absolute value of h is actually negative h. The limit h goes to 0 minus negative h over h, which is minus 1. So what do we gather from this calculation? Well, we gather that my function f here is both left and right differentiable at 0. However, these limits are not equal, which means that my function is not differentiable at 0 because that limit does not exist. When I put these two together, I get a limit that does not exist. That's one of your main examples of a function that is actually continuous across 0, but is not differentiable there because it has a corner at 0. Something like that. As one more example, we can look at the function f(x) equals sine of 1 over x, as long as x is not 0, and f of 0 is 0. And again, look at this derivative at 0. So I'm looking at the limit as h goes to 0, f of 0 plus h minus f of 0 over h. F of 0 is just 0. I know how to plug in for f of 0 plus h, it's just going to be sine of 1 over h. And so this becomes the limit as h goes to 0, 1 over h sine of 1 over h. Now what do we know about this limit here? Well, we know from our work previously that the limit as h goes to 0 of sine of 1 over h does not exist. This is our main example of a divergence by oscillation. Sine of 1 over h goes back and forth between minus 1 and 1 super fast as I approach 0, so this limit does not exist. Now if I were to scale this fact by a 1 over h, that's going to make it even worse. That's going to now go back and forth between numbers that are getting bigger and bigger and bigger as we go closer to 0. So it's going to go from minus 1 to 1, minus 2 to 2, minus 3 to 3, and just keep getting bigger and bigger as they get closer to 0. So this limit here is going to look something like this. Right, so my function is going to start coming in, and the oscillations get bigger and bigger and bigger. I'm going to run off the page, but they're getting bigger and bigger, and they're getting closer and closer together as I approach into 0. So this limit here is not going to exist, and the one-sided limits also don't exist because they didn't exist for the first case either. This function is neither left nor right differentiable at 0. And so therefore it's not differentiable either. That's the idea of one-sided derivatives and how you can use them to help with these calculations and also figure out why certain derivatives don't exist. Right? The fact that absolute value doesn't have a derivative is not because the one-sided limits don't exist. It's because the one-sided limits are not equal. And that's what makes that derivative not exist. So this gives you another way to look at these limits and figure out why they don't exist and how they behave. seeing a better idea of how these functions actually look like if you were to draw them out or try to analyze what they look like as graphs.